Hello, you're welcome to our SPI lectures. This is Negedi Godwin again, and we've been dealing with issues around sound parameters and sound waves. So today we're going to look at velocity or propagation of propagation speed of sound. Now, if you are just learning SPI to be a better sonographer, or you are joining us in preparation for an exam, this is where you should begin to pay serious attention, because we're going to be dealing with things that are necessary for most parts of your exams and interaction with diagnostic ultrasound. So, velocity or propagation of sound, propagation speed of sound, is the rate at which the sound wave travels through a medium. So what determines the speed of sound? The speed of sound or velocity of sound through a medium is determined by the physical characteristics of that medium through which it is transmitted, not by frequency of or wavelength. So how fast sound travels through a medium depends on the property, the density of that medium. Never forget. Speed of sound is determined by medium. I've said that again. This means that different media propagate sound at different speed. So let's look at the table below and see velocity of sound in soft tissue, air, and other body tissues. So here we have air. The speed of sound in air is 330 meters per second. In fat is 1,460 meters per second. In water is 1,540. This information is very key because water at 50 degrees and soft tissue seem to have the same speed of sound. Of liver, muscle, and bone, all of them have their various speed of sound in them. For diagnostic ultrasound, you should know the ones which are indicated with the asterisk. So these ones are for the air, the fat, the soft tissue, muscle, bone. You can see a trend in the above list that sound travels fastest through stiffer medium and slow through media that are more compressible. Sound travels fastest through solid, more slowly through liquid, most slowly through gas. So let's go back again and see the speed of sound increases downward and decreases upward. So it's fastest in bone and slowest in air. Take note of this information. What are the properties in a medium that affect the speed of sound? Number 1, stiffness. Number 2, density. This information is very key. You always, almost every time, see that in an exam. But besides exam, you need to understand that the two physical characteristics of a medium which determines the velocity of sound is the stiffness, that is resistance to compressibility. Like bone does not compress, so it's easy for sound to vibrate through it. fast, and of course it has a very high density. So stiffness and density. The velocity of sound is directly proportional to stiffness of the medium and inversely proportional to media density. Here you have the equation, velocity equation. The velocity of sound is equal to stiffness over density. We can express this relationship slightly different by using the term compressibility or elasticity rather than stiffness. However, since both compressibility and elasticity are opposite of stiffness, the relationship can be expressed as velocity of sound as inverse density and velocity of sound inverse density times elasticity. So it's just the inverse proportionality of these two properties. The stiffness of a medium is due to the strength of its intermolecular bond. If the molecules are tightly bound to each other as they are in solid, then the medium is stiff and the propagation speed through the medium is high. On the other hand, if the intermolecular bonds are weak as they are in gas, then the propagation speed through the medium is slow. Density also plays a role. Density is the mass of the medium per unit volume. The higher the density of a medium, the more mass it contains with a given volume. The unit of density is kg per cube of a meter or centimeter. Denser medium propagates slowly because they have more mass per volume, per unit volume. This makes it much more difficult to get molecules moving, and thus the sound wave propagates more slowly. The reason why sound does not propagate pretty fast in air. It's a trade-off between stiffness and density. The stiffer the medium, the higher the propagation speed. The denser the medium, the lower the propagation speed. Solid propagates sound faster than liquid or gases because while they are denser, which would slow down the speed, they are much stiffer. It is the stiffness of the solid material like bones that gives much higher propagation speed. So the speed of sound in soft tissue, let's pay attention because we're going to be dealing majority of our activities on soft tissues in diagnostic ultrasound. The difference in density and stiffness between soft tissue organ of the body, example like the liver, spleen, kidneys, are very small. Therefore, the velocity of sound in human soft tissue is taken to be a constant at 1,540 meters per second or 1.54 millimeter per microsecond. You need to take note of the units and the conversion of the units so that you don't get confused when it's asked. This value is very important because it is the calibration value used by ultrasound machine to calculate distance on display. All ultrasound machines assume the velocity of sound is constant, which allows the instrument to generate images. So all ultrasound machine operates on the assumption that all the tissue have the same speed of sound. Of course, we know they don't all have, but for practicability, that assumption is done. All right, very important information, range equation. The sound imaging instrument operates on pulse echo principle. A pulse of ultrasound is sent into the body from a transducer. The pulse travels down into the body at the propagation speed of sound in soft tissue. Remember, 1540 meters per second or 1.54 millimeter per microsecond. Tissue interfaces produce echoes which return to the transducer for processing. On returning to the transducer, the ultrasound system assesses the amplitude of the echo, and using the time between transmission and reception, it calculates the depth of the originating interface. To calculate the depth of each echo, that's the distance of the tissue interface or reflector, the ultrasound system uses the range equation. And here we have distance equals to speed times time divided by 2. That's the range equation. You remember when we are in our introduction, when we're discussing how the system of the converter write and read, this the formula that applies to that information. We'll see more of that in the coming lessons. So here the time is the time between the transmission of the pulse and the reception of the echo. This time is also called pulse echo time, pulse round trip time, time of flight, go return time. Most popular is go return time. So wherever you hear any of them, it means the same thing. The speed is the velocity of sound in soft tissue, which is 1.4 millimeter microsecond. This value is programmed into the system and does not change. It is called calibration speed. The 2 in the denominator of the equation is because the system only wants to calculate the distance to the interface, not the distance to and fro the interface. I hope that is clear. They just want to know the distance, not the round trip, just a single trip. So here we go. Reflector distance is the constant 1.4 millimeter microsecond by the go return time, which is in microsecond. So distance is directly proportional to go return time. Now deep echoes will have long go return time. Superficial echoes will have short go return time. And that is very simple to understand. Nothing much to say. So let's look at amplitude, power, intensity. All these are very key. In fact, all these are interplaying without your knowledge in your ultrasound machine. So it's important you know what's going on. Amplitude, power, intensity relates to the strength of the sound wave. There are 3 different ways of expressing the strength of sound wave. Each does it in a slightly different way, but all 3 are related to each other. Amplitude. The amplitude of sound wave is the strength of the wave or peak height of the wave. It is the difference between the maximum value of acoustic variable and its resting value, or when no sound applies. In a sine wave, amplitude is the distance between the baseline to the peak of the wave in the plus direction, or the distance between the baseline to the peak of the wave in the minus direction. Simply put, is the height of the wave. Amplitude of a sound can be described using any acoustic variable like pressure, density, temperature, and particle motion. The most commonly used variable is pressure. The unit for amplitude will depend on the acoustic variable being measured. So if you are measuring pressure, the unit is Pascal or Newton cube meter per cube meter. Particle motion, if it's particle motion, we're looking at micrometer. If you're looking at density, it's gram per cube centimeter. The temperature, of course, is in degree. However, when we want to express ratio between two amplitude or two power or two intensities, we use the unit decibel. The initial amplitude of a sound wave is determined by ultrasound system. The greater the amplitude of the voltage applied to the transducer, the greater the initial amplitude of the ultrasound wave produced by the transducer. Remember our diagram, we'll get back to it again, but if you go back to that video, you'll notice what happened. What does the pulsar do? The pulsar sends pulses of voltage. So if you apply that knowledge here, say the greater the amplitude of the voltage applied to the transducer, the greater the initial amplitude of the ultrasound wave produced by the transducer. The amplitude of the sound will decrease as the ultrasound travels through tissue. Remember attenuation? This loss in amplitude is called attenuation, which we'll discuss more in later detail. Increasing the amplitude of the outgoing ultrasound wave increases the depth. This allows the system to receive and display echo from more distant interface. That's when you're increasing the frequency. When you're increasing the amplitude, when you increase the amplitude, the frequency reduces. The amplitude of ultrasound is controlled by the output power control. A higher electrical voltage causes the transducer crystal to vibrate more strongly, producing a higher amplitude ultrasound pulse. This control button on the machine is commonly labeled as power or output. Power in a sound wave is defined as the rate at which energy flows through the medium. It is the rate at which work is performed. In case of ultrasound, the work performed is the production of the ultrasound wave by the transducer and the propagation of wave through tissue. The ultrasound wave contains mechanical energy which vibrates the molecules in the medium. The more power, the stronger the vibration, and the farther the sound will travel in a tissue. So the unit of power is watt, milliwatt. A milliwatt is 1/1000th of a watt. The decibel may also be used to describe relative acoustic power. That's the ratio between two power. All electrical appliances and electrical systems have a power rating. They use power to work, like your toaster, your stereo amplifier, and also. So an ultrasound transducer takes electric power and converts it into mechanical energy of sound. The relationship of power with amplitude. This is the formula. Power proportional to the square of amplitude. This is how they relate. Power is proportional to amplitude squared. If the amplitude is increased by a factor of 2, then the power is increased by the square factor of 2. The power is increased by 4. Thus, amplitude is increased by a factor of 3. Power is increased by a factor of 9. That is a square of 3. And so on and so forth. So from the information, from the equation, you know that Once your power is increased, the amplitude is squared up. That's how it's done. Make sure you know this relationship for RDMS registry exam. It's very key. You will not miss it. So take a look at it again. So power is related to intensity and area as follows. Power is equals to intensity squared. Power is equals to intensity, that's watts centimeter square, but multiplied by area, the square centimeter. So intensity, therefore, is the concentration of power in area. In an area, concentration of power in an area is intensity. Is the power in a beam divided by the beam's cross-sectional area. This is the formula. Intensity equals to power measured in watt over area measured in square meter, centimeter square. The unit for that is watt over square centimeter, milliwatt over square centimeter. Decibel unit can also be used for intensity when we want to compare two intensities. From the above equation, we can see that power is directly proportional to intensity. Thus, an increase in power will result in increase in intensity. Increase in power by the factor of 3 results in an increase in intensity by factor of 3. Beam area also has a role. Area is the denominator of the equation. There is an inverse relationship between beam area and intensity. If area decreases, intensity decreases. For a given power level, intensity is greatest where the beam area is smallest. Where the beam area is smallest, intensity is increased in that area. In other words, there's a convergence of sound on that particular point, focal point. We'll get to that point in the studies. This region is called a focal point. Thus, ultrasound beam intensity is highest in the focal point. That's why when you're using your machine, please know where your machine focal point marker is, and you can adjust it to your area of interest for a higher resolution. This understanding is important to avoid biological effect in body tissue. So let's summarize this quickly. Intensity is directly proportional to power. Intensity is inversely proportional to area. Power is proportional to amplitude squared. Intensity is proportional to amplitude squared. Now, given a constant beam area, if power is doubled, intensity is doubled. If power is increased by a factor of 4, intensity is increased by a factor of 4 because they are proportional, right? And so on and so forth. So if power is reduced by 90%, intensity is reduced by 90%. So given a constant power, if beam area is increased by factor of 2, intensity is reduced by a factor of 2 because because of their inverse proportionality. If beam area is reduced by a factor of 3, intensity is increased by a factor of 3. If beam area is increased by 20%, intensity is reduced by 20%. So remember that the intensity increases where the beam narrows and vice versa. If beam area is halved, intensity is doubled. So we'll continue our lectures with bioeffects, power, and intensity in our next discourse. So do have a great day, but make sure you sign up for our paid class where we deal with specialties like abdominal, gynecology, sonography, obstetrics, and small parts, which include scrotum, thyroid, and breasts. Thank you.